So this video then is section 9.3, is the second video on chapter 9, but really the first half of chapter 9 is a separate topic. We're kind of, we could start chapter 9 here just as well, apart from the fact that we need, in order to get one of the 5 formulae we're going to deal with, it's helpful to understand the velocity time graph a little bit. What I'm going to do is I'll start by explaining the formulae that we're going to use and where they come from, and then probably in the second video I will go on to how to solve the questions. Okay, so this one is really an introduction to the topic. If you've tried it already and you're stuck, you may well want the second half of this video, or possibly just have a look in the playlist. I may well be onto a second video for examples of actually how to do them. So I've said already in the previous video that speed equals distance over time is something we'd use for a constant speed. So now we're making that a bit more complicated. We're not talking about speed, we're talking about velocity, and we are going to deal with a constant acceleration, not with a constant velocity. So the things that we deal with are called S, U, V, A, and T. S for displacement, U for the starting velocity, V for the final velocity, A for acceleration, and T for time. Okay, so those are all the things that are involved. Acceleration is a change in velocity. So if there is an acceleration, we have to start at one velocity and finish at another velocity. Okay, the movement that we're measuring happens over a certain time and happens over a certain displacement. So displacement, initial velocity, final velocity, acceleration, and T for time. You'll notice that I've underlined these ones because these are the vector quantities. Okay, so like putting vectors in bold type or underlining them. I'm a bit of a stickler for underlining my vectors. I care about it. I think it's important to distinguish your vectors from your non-vectors, and you'll probably in these videos, I will do an example where I forget to underline the vectors. So that'll tell you how sort of unimportant it is. Almost nobody bothers worrying about underlining these vectors. I bother about it quite a lot, and even I forget. But that's us doing it properly for the first example. These 4 are vector quantities, and T is time. Now, in this chapter, we're dealing with only one-dimensional situations. So we're just moving along, to start with, along horizontal lines. So we'll pick a positive direction. Often we'll draw a diagram so the positive direction is moving to the right. So these are vector quantities in the sense that they are either positive or negative. Okay? They're moving in the positive direction or moving in the negative direction, that's all there is to it. There's no more complicated vectors than that. We'll deal with these things as as 2-dimensional vectors later on in the course, but for this chapter, 1-dimensional situations. So if we have an acceleration, if it's a constant acceleration, and we start at an initial velocity u and we end up at the final velocity v, well, acceleration is by definition the change in velocity over time. How many meters per second are you increasing or decreasing your speed by every second? So the change in velocity is your final velocity take away your initial velocity, v minus u, and if you divide that by t, that is your acceleration, isn't it? Change in velocity over time. So that one is really just a definition. Now I like to remember that formula that way around. You can see it in the book here, and they rearrange it into the form that most people like it, v equals u plus at. Okay, so v equals u plus at just comes from the definition of acceleration. The reason I prefer to remember this one is because it is the definition of acceleration, so it's not really easy to forget it. It's change in velocity over time. V equals u plus at if you like. Even this one, I suppose, is pretty intuitive. It's the initial velocity. Oh, sorry, I've got my underline right, haven't I? The initial velocity plus so many seconds times so many, times the acceleration. So if you're increasing your speed by 3 meters per second every second, well, if you started at 10 meters per second, if you're increasing by 3 meters per second every second, and you go for, say, 5 seconds, then that's 5 lots of 3 meters per second. That's how much you've increased by. So you start at this speed, you increase by that much, and that will tell you your final velocity. So even this version is fairly intuitive, but for me this one is even more intuitive, so I like that one. The second sort of straightforward equation comes from here. If we think about a constant velocity situation on a velocity time graph, I'm going to draw my line here because there's no need to sort of start off at the axis here. Maybe it's a little bit clearer if we do, but I'm just going to make the point by doing this. We have an initial velocity and a final velocity, u and v. the time taken is this distance here, okay? So the area underneath this curve is the displacement. We know that from the previous section. So the area under this curve is, well, it's a trapezium, isn't it? So these are the two parallel sides, so add those up, u plus v, half the sum of the parallel sides, times the distance between them, and this distance here is the time we've taken. So u plus v over 2 times t. So those are our first two equations, okay? So I'm just going to write those out again. V equals u plus at. Oh, I keep putting the underline on the t. And s equals u plus v over 2 times by t. Now, I promise that the order I'm doing this in is I'm going to show you all 5 of the equations, and then we'll talk about how to use them. In practicing this, I would suggest that you again can think of the next two exercises, 9c and 9d, you can think of as one big exercise. The techniques for solving those questions is exactly the same. The reason they split it up is because for 9c, in the book, they've only introduced you to 2 equations, and that's the 2 that we've just found there, okay? So for 9c, you know you can solve all the questions with just those 2 equations. It's not always the best way of doing these 13 questions. Sometimes there are better ways, but you can solve them with just those 2 equations. When it gets to exercise 9d, we've got 3 more equations, so we might want to consider all 5 equations. Well, we will have to consider all 5 equations in order to be able to do the questions on 9d and the questions thereafter in the chapter. But I'd suggest you think about them as one big exercise, because the technique for solving the questions is exactly the same. It's completely identical, and when you get to the exam, you treat all those questions as the same thing, right? So we've said already SUVAT, which is, by the way, why some people call these the Suvat equations, SUVA and T. Those are the 5 things that we've got, and the questions will always give us 3 of these things and ask us to find a 4th one. So if you look at these equations, the 2 that we've got 1, 2, 3, 4 things in this equation. We've got 1, 2, 3, 4 things in this equation. You'll notice that this equation here doesn't have a displacement in it. This equation here doesn't have an acceleration in it. And the way that this works is there are 5 equations. 1 doesn't have an s, 1 doesn't have a u, 1 doesn't have a v, 1 doesn't have an a, 1 doesn't have a t. Okay, so that's what the equations are that we look at. So if we look at these 2 equations, if I want to make an equation without a t, well, there's a t in this one and there's a t in this one. So I can treat that as equation number 1. I could rearrange this to 2s over u plus v equals t. I can treat that as equation 2, and I can substitute equation 2 into equation 1, and I'm going to get v equals u plus a times, this is t now, isn't it? So 2s over u plus v. Okay, now that equation now does not have a t in it. It's not a particularly nice equation, but it doesn't have a t in it. Now, excuse me, there's the clock going again. So if I rearrange this equation, I'd end up with this one here, okay? Now you'll notice that the substitution that I've done is a little bit different to the substitution in the book. If you're interested, I'm going to leave that there for you. You could try and rearrange this equation. It should end up as v squared equals u squared plus 2as. If you're not interested, it's fine. You don't need to go through that. You can look at this derivation in the book. But the point I'm trying to make to you is they've taken these 2 equations, they've treated them as simultaneous equations, and they've eliminated the t. Okay, so they've substituted from one equation into the other for t, and that gives us v squared equals u squared plus 2as, and as promised, there's an equation without a t in it. If I go back to these 2 equations and do the same thing for v, so if I take this equation, we've got a v in there, so I'm going to write this equation out, only instead of writing out a v, I'm going to write u plus at. So s equals u. Instead of v, I'm going to write u plus at. All of that over 2 times by t. Okay? So if I take that, and that's what the book's got, and then if I would just work from there, This is u plus u is 2u. I can split this up as 2u over 2 and at over 2 and expand the brackets out with a t. So I end up with s equals ut plus a half at squared. Okay? So we've got an equation without a t, we've got an equation without a v, and if we wanted an equation without a u, then we can eliminate into this formula, we can substitute into this formula, sorry, from u, and how do we get u? Well, we go back up to here, and we see that u equals v minus at. That can get stuck in there, and there's our last equation. So here are our 5, we just about rescued that. So here are our 5 Suvat equations. For each of our 5 variables, s, u, v, a, and t, there's one equation without them, okay? And in the second video, I will start talking about how to actually use these equations and what the approach is, which will deal with pretty much all questions that you've got on Suvat, but also in broad outline, it's the technique for all questions more or less in mechanics. So here we go.